Marker. And does anyone have any questions before I get started today? To make sure, I want to make sure, I'd rather move slower and make sure that everybody understands than just kind of barrel through. So we're going to change direction a little bit. So we were talking about Cantor series last time, and these are very different than most numeration systems or expansions that are dealt with by people. We're going to look at some more classical things like continued fraction expansions, beta expansions, Lüroth series expansions, and there's some generalizations of Lüroth series expansions that some people in this room have dealt with. And I wanted to mention like an itty little bitty bit of ergodic theory. I don't want to say too much about that, but just to kind of say something, and you can go off and do more of that if you want to. So let's look at another numeration system that's very, very important all throughout math. And it's not because it's a numeration system sometimes, but it has many, many applications. This is called the, let's say, regular continued fraction expansion. And there are many, many types of continued fractions, so there's other ways we can handle this. And for simplicity, let's assume that x is in 0, 1, minus q. We can still talk about continued fraction expansions of rational numbers. Every rational number will have exactly 2 expansions. Every irrational number will have one unique expansion, and it's of the following form. You can write x, let's say symbolically in the form of a1, a2, a3, and so on, where an is a natural number, and here we're starting counting at 1. So Ukrainian and American way, not Polish way. We start counting at 1 with this, for the natural numbers, just like with the floors here. And we write this as follows: 1 over a1 plus 1 over a2 plus 1 over a3 plus ... Exercise, this converges. So just to make sure I'm not writing some sort of nonsense, I have this expression. Clearly this is a limit of some sort, so you can take it as an exercise to interpret exactly what's going on here and to prove that the limit actually converges to something, because maybe it wouldn't. So we need to be very careful a lot of times when we have some way we want to represent real numbers. Does it actually really mean anything? So here it does, so it's an exercise. And so this is a little bit different than say like something like a B-area expansion, where we have finitely many digits. Here we have countably many. But it's also different than a Cantor series expansion, because at every step we have countably many possible digits we can see. So in a Cantor series expansion, at any position you only have finitely many possible digits. So in some ways it's kind of less complicated what the space is right here. So it's actually the so-called bare space. Bare space. N to the n. This is something set theorists care a lot about, and this actually gives this mapping. If you map some sequence in n to the n to a continued fraction expansion, this gives a nice bijection between the bare space and the set of irrational numbers. So this mapping, say if you take a member, let's say S is a sequence, so this is some sequence of integers, and if you map S to, let's say, the continued fraction expansion, how do we want to call that? Let's say S is a1, a2, and so on. If you map S to 1 over a1 plus 1 over a2 plus ... this is a bijection between the bare space and the irrational numbers in 0, 1. So this is actually one reason set theorists care about continued fraction expansions. I promise this is in many areas of math. So independent of what anyone here cares about, that's already something of interest to set theorists. There's other ways of doing it, but this is a very natural and simple way. So you could ask like a student, for example, I don't know which class, but let's say in some class, find a bijection between this set and the real numbers and write it down explicitly. And maybe without this hint, maybe it's a hard question. I actually don't know. I never tried it without that hint, because I didn't even think to write that down until someone said, oh, this is a bijection. So let's do a simple example. So I will give this Oh, 1 over 1 plus 1 over 1 plus 1 plus 1 over 1 plus dot dot dot. Any ideas?
Golden ratio.
What is it?
Golden ratio.
Yeah. And why is that? We can say x equals 1 over 1 plus x. And this will be like 1 over golden ratio or something because like we restricted this to be between 0 and 1. If we added a 1 here, it would be golden ratio. So we just solve this quadratic, we solve. And yeah, we get, I think it's minus 1 plus root 5 over 2. So symmetry helps us. So this is a simple example, and it turns out that a continued fraction, I'm just going to write CF because I don't want to keep writing continued fraction. A continued fraction expansion is, say, a continued fraction, let's see, the continued fraction expansion of x is periodic if and only if x is a quadratic irrational. This is due to Lagrange, is that correct? Is this Lagrange that proved this? I think so.
It's more or less clear because of the same argument.
But one of the other directions is harder. So one direction is easy, then the other is difficult. I forget. So one of them you can do this type of thing, but to go, so either way, this is true. I believe it's believable, let's say, but I don't want to say that the theorem is going to be quite so easy. You might run into some problems proving it. So, what about something like cubed root of 2? Any ideas what happens?
Nobody knows, even Tron.
Yep. Completely unknown what goes on. Yeah, it's a mystery. So these any algebraic numbers of degree 3 or higher, it's not known what happens. Probably these are normal numbers for continued fraction expansion, and we have not defined what that means yet. So we're going to get to that. So there is some information known about this. There's a paper in Acta Mathematica by Bajot and Adamczewski where they show that the block complexity function is superlinear for cubic and higher irrationals, which is a very interesting result. They have something similar for quadratic irrationals and higher in base B. And this is kind of considered this, I don't think I mentioned this Borel conjecture. There's this very important, I would say this is one of the biggest conjectures in the field of normal numbers, is that every algebraic irrational number is normal in all bases. So Borel conjectured this. So for example, square root of 2 should be normal in base 2, base 3, base 4, and so on, base 10, base 20. And there's like a tiny, really little bit of evidence towards this. This is due to Adamczewski and Bajot. They showed that the block complexity function is superlinear, which is so incredibly far from settling this conjecture or even beginning to attack it, but it was already enough to be an annals paper. So that says kind of how difficult and this conjecture is, and probably it's the case as well for continued fractions. So what is a normal number for a continued fraction expansion? So let me ask this question. Roman, do you know? Does anybody know?
Could you please repeat your question?
How do you define normal number for continued fraction expansion?
In the same manner. Should consider Gauss distribution.
Yeah, okay. We have a measure. We can say mu of I is 1 over log 2. Where this comes from, we're not even going to attempt to talk about today, but I'm going to at least define it. So let's say I is a subset of 0, 1. So remember when I wrote the definition of uniformly distributed mod 1, I intentionally put the Lebesgue measure there and said, okay, well, this is just the length of the interval, but we can replace this by something else. So let's take definition, is that x is continued fraction normal, and I'm going to kind of unpack this and say what this means. If the sequence t n x is mu uniformly distributed mod 1, where tx from, let's say, 0, 1 minus q to 0, 1 minus q is defined by tx equals 1 over x mod 1. So this is mysterious. What's this tx doing? And I claim this is just the same thing as multiplying by 10 in base 10, right? You shift.
One shift.
Exactly. Because if you have this expression right here, or like let's say this, let's say you invert it, and then we get a1 plus all this. Well, a1's an integer, we just throw it away and we get this right here. So we're shifting. Now this map, how does this look when we graph this? It's a little bit more interesting. So we have 1/2 to 1, and then we have 1/3 to 1/2, 1/4, 1/5, and so on and so on. And it looks like this, that, and like that, and so on. And we're going to call this interval 1, 2, 3, 4, and so on. So we have this kind of question because, just like before with Cantor series expansion, we have infinitely many digits. Just even asking what should we expect? How often should 1 show up? How often should 2 show up? And so on and so on. Well, for a Cantor series expansion, you kind of get this intuition that, at every step, every digit should be equally likely to show up. But for continued fraction expansion, not really. We think that, because what's the first digit of a continued fraction expansion going to be? Well, if x is here, the first digit's going to be 1. If x is here, the first digit is 2, 3, 4, and so on. And these intervals are shrinking. Right? So they're shrinking quadratically. Right? Because if this is something like 1 over n minus n plus 1, 1 over n minus 1 over n plus 1, right? This is going to be 1 over n times n plus 1, or approximately 1 over n squared in length. Right? So they're going down quadratically. And so just from there, we should probably get the idea, well, we're not going to see, for say, Lebesgue almost every x, we're not going to see the same frequency for all the digits, which is a good thing because then they're not all just going to be 0. What's it going to be? And this particular measure, where does this come from? That's a very hard question. We're not even going to try to answer. But it's the only measure that's going to be invariant with respect to our transformation and ergodic and equivalent to Lebesgue measure. And I'll define ergodic in a little bit and talk about the ergodic theorem very, very briefly. But there's basically one right measure, because what we want is we want to talk about what's going to be the behavior for almost every digit. So almost surely what's going to happen for the digit 1, the digit 2, the digit 3, and so on. And there may be any sort of crazy behavior. You can cook up a number with any type of crazy continued fraction expansion. But you want to talk about what happens almost surely if you pick a real number uniformly at random in 0, 1. And notice this measure here, this is almost the same as Lebesgue measure. So, what does this mean for those who, say, haven't studied any measure theory? All we're really doing is, it's just think of this in probabilistic terms. The probability that you land in this interval I is just going to be the integral here. And you divide by log 2, because if you integrate the entire interval, you get log 2, and you want everything to just be a 1 in total. So this is kind of boring right there, what's going on. So if you have a continued fraction normal number, how often does the digit 1 show up? And that's pretty easy. So it's going to be more complicated, but it's still not that hard. So the frequency of 1 in a continued fraction normal number is, let's say, mu of the interval 1/2 to 1. So we just apply this measure to this interval here that gives you the digit 1. So this is going to be equal to 1 over, and you can just take this as an exercise, 1 over log 2, integral from 1/2 to 1 of dx over 1 plus x. Very, very easy exercise to compute this, but you should still do it anyways because silly things like this build intuition. So it really helps to just do that. But this is approximately 0.415. So about 41.5% of the time you're going to see a digit 1. You can write it exactly, though. You don't need to approximate it. That's just what you get when you put it in a calculator. Okay. And then it's going to be, I forget what it is for 2. You could just change for the digit 2. It would be from 1/3 to 1/2, and so on and so on. And it gets quite a bit more complicated what happens when we look at blocks of digits, because previously, say in a B-area expansion or a Cantor series expansion, we have an independence of digits, and here we do not. So let's figure out right now, I just want to actually figure out the interval where we're going to see 1 followed by a 1. So let's consider walk, let's say 1 followed by 1. So I don't mean 11 because 11 is a digit, because every natural number is. But here I mean just a 1 and then a 1. Okay, so for starters, where is that going to be? We know that it's going to be somewhere between 1/2 and a 1, right? Because the first digit is a 1. Okay? But then we need to be mapped again to 1/2 to 1. So we have our mapping 1 over x mod 1. And we need to look over here, 1/2 to 1. So there's going to be some place here. And when we project this down, this interval right here is going to be where we have 1, 1. Does that make sense to everybody? And we can just do a little simple algebra to solve it. Because we start with the 1 here, and this means as well, if you're looking at where we have a 2 followed by 1, right? It would be a similar sort of idea here that you would go like this, and you would see, look at this interval right here. And that interval would correspond to 2 followed by 1. So what we need to do then is we need to figure, okay, so this graph right here, we're starting at 1/2, and we want it's like 1 over x. 1 over 1/2, that's 2, so that means on this portion right here, this is going to be the graph as 1 over x minus 1. So we have 1 over x minus 1, and we solve 1 over x minus 1 is equal to 1/2, right, to get this point right here. And so this is just 1 over x is equal to 3/2, or in other words, x is equal to 2/3. So just to be clear that, since this can be piecewise defined, here it's 1 over x minus 1, and here it would be 1 over x minus 2, and so on and so on. Okay, so that means the frequency of 1, 1 is going to be 1 over log 2, integral from 1/2 to 2/3 of dx over 1 plus x. Okay, makes sense. And you can, so exercise, this is also simple. This is not equal to 1 over log 2, integral from 1/2 to 1 of dx over 1 plus x squared. Right? If we had independence of digits, then the two would be equal, but they're not. So, like I said, just kind of actually do this by hand and just put it into your calculator or something, like you don't have to do anything sophisticated, and just see for yourselves like these things don't match up. So continued fractions, like I said, they're all over the place. There's also a lot of connections to number theory, Diophantine approximation, to geometry and random things, and hear about them from the perspective of a normality. It turns out that, Lebesgue, almost every real number is continued fraction normal. So we know that almost every real number is normal in every integer base, and Lebesgue, almost every real number is continued fraction normal. This is from the Ergodic theorem, which I hope to have time to talk about a little bit. So what about giving an example of a number that is normal in every base and continued fraction normal? This was actually an open question for a while.
Almost all numbers.
Yeah, almost all numbers will work, yeah. There will be some many non-computable examples as well. So a computable example of a number that is normal in every base and also continued fraction normal. This was first done by, so number that is normal in every base, b greater than or equal to 2, and also continued fraction normal. And the first example was due to Adrian Shearer. I think I spelled that right, in 2016. And it is not published in the journal. He left math, unfortunately, so you can only find it on archive. and he had a big O of 2 to the 2 to the n algorithm. There's also Betcher, and I forget her co-author, this is completely unfair, plus co-author, so don't tell her I forget who her co-author was, but she has and her co-author have a big O of n to the 4th algorithm, so they improved it a lot. You can come up with examples of, just actually examples in the first place of continued fraction normals are much more rare. The best example is due to Adler, Keenan, Smorodinsky from 1981, or best in terms of like the nicest to write. I have an example with Manfred Modrich. When was 2016 it was published. We submitted the paper in 2012, and it took 4 years to publish it. It's up there. It's on Monet-Schefter. And the paper does a lot of other things as well. One of them, it's a very, very, very inefficient, very ugly example of a normal number for a continued fraction expansion. But it does a lot of other things at the same time. But I would say the best example, Adler, Keenan, Smorodinsky. And I think this was 1981 in Journal of Number Theory, so this is like published when I was born. And they look at the following sequence: 1/2, 1/3, 2/3, 1/4, 2/4, 3/4, and so on. And then I didn't say how to get a continued fraction expansion of a rational number, but you can do the same process. It just stops at some point. And it's actually really nice because you just take any of the two, these will have two continued fraction expansions. You just take any of the two continued fraction expansions and you concatenate them to get one big long continued fraction expansion. And that number is normal for the continued fraction expansion. So I think that's nice. That's the easiest to write down. Everything else is much uglier. Van de Heij, this is the best. Van de Heij had some tweaks to improve it a bit. I forget when he published it, so him and I have talked about a lot of things, so I always forget when it was published and when we discussed it and he actually solved the problem. But you can look up, he's done a lot of very interesting stuff with normal numbers. What about the following? If x is CF normal, is 2x CF normal? This was also an open question for a while. If you take a normal number and for continued fraction expansion and multiply it by 2, do you get a normal number back or not? What do you think? There's no guarantee of this, right? Because we saw in the last class for Cantor series normality, multiplying by 2 may not preserve it. For base B, it does. And for continued fractions, like there's many, many ways that a continued fraction is much better than the decimal expansion, right? The reason we use decimal expansions is because of counting money and doing calculations and things like that, right? So we have very simple algorithms for like adding, multiplying, dividing, subtracting. For continued fraction expansion, we don't. Just something like multiplying by 2 is horrible.
Multiplying by 2 change frequencies of all digits drastically.
Well, it doesn't, as it turns out. That's kind of the question. So does it change?
Maybe yes.
So if you're given something like x, right, it's 1 over a1 plus 1 over a2 plus ... then 2x is going to equal what? It's totally mysterious. So how, if you're given this expansion, so for something like a decimal expansion, and you can multiply by 2 and use the expansion to very easily come up with something. For here, I see nothing simple you can do. Whatever you get over here is going to look totally different than what you have here. There's no simple algebraic trick to just put a 2 down here or something. It just ends up being totally different. So if you don't believe me on that, it could be a good exercise to say, just try random numbers, write a little computer program, spit out continued fraction digits of one number and then 2 times that number and see how they relate and just see that they'll be a bit different. So there is an algorithm, but it's nothing quite so simple as we're used to, but also due to Van de Heij, so I really like this result. So I like to always talk about it. Suppose that A, B, C, D are integers, and the determinant of A, B, C, D is non-zero. continued fraction normal. Then ax plus b over cx plus d is continued fraction normal. So I like this result. It's very nice. This was published in Compositio in 2015, I think, or maybe it was solved in 2015 and it was published, because I was talking with him about this about 10 years ago at a AMS sectional meeting. So very nice paper, very, very dynamical, lots of ergodic theory and related stuff. So just a warning, it's a nice paper, but it's not, from my perspective, an easy read just because it's a complicated and interesting theory. But there's also some stuff missing because, do we know what's the set of numbers that preserve normality under addition? We don't have a classification. So unlike with B-area, so in some ways this is stronger because we don't have a result like this for decimal expansion. But we also have full characterizations of which numbers preserve normality under addition and which numbers preserve normality under multiplication. By the way, for those who know, we'll hopefully talk to it. There's nothing known like this for Lüroth series. It's totally, what would the right function be here for Lüroth series? No idea. Maybe it's a fractional linear transformation, maybe something else. So.
It was published 10 years ago in which?
Compositio.
In Compositio.
So this is a nice journal. So you can just look up Van de Heij and MathSciNet and find a bunch of interesting stuff. I think he's done a lot of interesting work. Let me write a couple other things down. I'm also going to also write another thing, also due to Van de Heij. Let's say the set of numbers. This is related to the next few lectures. The set of numbers that are continued fraction normal, but not normal in any base, is uncountable. And this is assuming GHR. GRH, generalized. So this is the generalized Riemann hypothesis, and that's a very, very, very big hammer to assume. So this is a conditional result in something that may very well be open for hundreds of years or more. Hard to say how long that's going to be open or if it's even true or not. But assuming this, we know that there are at least numbers that are continued fraction normal but not normal in any base. And what's the Hausdorff dimension? So let me maybe ask something like this to Professor Torben or others.
Sorry, could you please misunderstand or misprint? The set of numbers that are continued fraction normal but non-normal.
Not. I think I said it but didn't write it, so I apologize here. But not normal in any base. Yeah, if it's just normal, then you're intersecting sets of full measure, and we have constructions mentioned over there. This is something harder because you have a set of full measure, then a bunch of zero measure sets.
What was your next question?
What's a Hausdorff dimension? That's a question for you guys that like Hausdorff.
Actually, I always show that full Hausdorff dimension.
Could it be full or 1/2? Or it could be full. It's very possible. I don't know. I'll believe your intuition on it. I have no idea. I don't know how to even begin answering the question. By the way, we did actually remove this generalized.
The set of those real numbers which are non-normal in any base, in any base in ascending expansion.
Yes.
Is a full dimension, so intersection with the set of full the back measure should be a full Hausdorff dimension.
Could be. Possible. We can say it's in some ways it's even stronger because a set of non-normal numbers is a winning game for is a winning set for Schmidt's game. So they do have this countable intersection property. So set of numbers normal and no base is already a full Hausdorff dimension set. But then the set of continued fraction normal numbers, it's full measure, but it's not a winning set. So you can't use Schmidt's game, for example, to get a result like this. Maybe there's something, you could do that could answer what the Hausdorff dimension is. I have no idea myself. I'd be very interested to see a Hausdorff dimension. So one thing we're going to be talking about in the next couple lectures is it is actually possible to remove this use of the generalized Riemann hypothesis. And very bizarrely, we were able to remove it by using tools from set theory. You wouldn't think that that would happen, but that's what happened. So there is an unconditional result, and this paper was recently accepted at Advances in Mathematics. So I'll talk about this a little bit in the next couple lectures. So this is one with myself, Van de Heij, and Steve Jackson. So set theory absolutely does interact in interesting ways, and that's part of what I want to build up to, because there's a lot of tools that are useful that people may not be familiar with that you could start integrating. But there's some other interesting things as well. I want to move on to some beta expansions and a few other things, but let's suppose that x is a1, a2, a3, and so on. What about y and is continued fraction normal? Then a, let's say, n times, let's see, this is a, let's say, r, a m plus r, a 2m plus r, a 3m plus r, and so on, is not continued fraction normal if m is greater than or equal to 2. So if you select the digits along a non-trivial arithmetic progression, you very interestingly get a number that is not continued fraction normal. You can try some special cases of this to get an intuition. This is also due to Heersink and Van de Heij as well. They investigated this. So this is very different than in base B. If you do the same thing in base B, say you take a Champernowne number or something in base 10, and if you write all the digits at positions that are congruent to 1 mod 7, you're going to get a normal number back, and that's very easy to prove. You can take that as an exercise. But things get more interesting with continued fractions because this no longer works, but the limits still exist. So every digit in every block still has a frequency, it's just described by a different measure. So depending on your choice of m and r, you're going to get a different measure other than Gauss measure describing what's going on. Normal numbers can be very, very delicate. There's a lot of these types of properties that people, even some very well-known people, have assumed without proof or kind of stated incorrectly. This includes Erdős, Copeland, Fürstenberg, either Shapinsky or Lebesgue and others that, like I said, it's really, really delicate because you move to a slightly different situation and things can fall apart in kind of surprising ways. So also to mention set of normal numbers for here, it's like I said, set of full measure, but then the set of non-normal numbers is full Hausdorff dimension. It's also a winning set. Just a simple proof that this is a winning set. The set of badly approximable numbers is a subset of the non-normal numbers, and the set of badly approximable numbers is full Hausdorff dimension or a winning set. Both of those. So that's pretty simple. And then also the set of normal numbers is a meager set. So the same type of thing happens as before with the area expansions. I want to move on to another expansion. So any questions before I move on?
The last result, who is the author of this?
So Heersink and Van de Heij. Some of these results, these Van de Heij ones, have a funny origin because with Van de Heij, we kind of have some discussions and I solve things he doesn't know how to do and he solves things I don't know how to do. So all of these were actually problems posed by me that I didn't know how to do and solved by him. So he has a very good intuition for continued fractions. My intuition's a little better in a different direction. So I think these were like discussed at some AMS sectional meetings in like 2014 or 2015. But yeah, generally, like stuff about continued fraction normal numbers, I would just say, look up Van de Heij on MathSciNet, start reading some papers, and you can find a lot of really nice stuff. Yeah, I originally met him. It was a talk. He was a PhD student at University of Illinois, Urbana-Champaign, and I mentioned this really ugly construction I had of a continued fraction normal number. It also gives you a Lüroth series normal number too, and so it's a, the general construction does rather. So the number isn't both continued fraction and Lüroth series normal, but it follows from a general construction. And he was in the audience, and he hated my construction so much. He got like really angry, and he made this like construction of a simply normal Lüroth series that he felt was better, and then it just kind of started us talking and discussing things, and and that was a long time ago, like 2011 maybe, 2010, yeah, I think 2011. Okay, so I want to talk about, let's see how we are on time. I think we might just have to delay the ergodic theory part till early next week, but that's okay. We can mix that in with descriptive set theory. Okay, what about something called a beta expansion? So beta is going to be a real number bigger than 1, and so this is something. Do you guys know? Do people here talk about beta expansions or not? I forget.
A little bit.
Okay, so I'll define it. So here's another way of generalizing a decimal expansion. Rather than changing your bases at every step, what if you have a non-integer base? And you get entirely different horrors and interesting phenomena that happen than when you go to a Cantor series expansion. So Cantor series, very different situation than what we're going to have here. So here we can say, okay, beta greater than 1 is a real number. We can define the following map. For simplicity, we're just going to do this for something like beta is the golden ratio, because there's some easy things we can do with this one. And go up like this. And then this last piece is not onto. So say this is 0 over beta, 1 over beta, and then this is going to be just 1. Right, which is not going to be 2 over beta because beta is like about 1.618. So it's something that doesn't quite line up properly. So this only goes like this far. And we can generate the following expansion. We can say something like a 1 of x is equal to 0 if x is in 0 to 1 over beta, and 1 if x is in 1 over beta to 1.
Beta is not equal to 2.
Yeah, here we're using just a golden ratio to start off with to illustrate it, because we can let beta be any, even an integer, but we get this lack of ontoness when beta is a non-integer. And you'll be able to generalize this idea to like higher beta when we have more intervals and all that. So what happens here, and then we're going to have a n of x is, let's say, we're going to call this t sub beta of x. A sub n of x is a sub 1 of t to the n minus 1 beta of x. So we end up getting some series. So we're going to have, you can just take it as an exercise. X is equal to the sum of a sub n of x over beta to the n. This is when x is in 0, 1. When we define these expansions, we have to make sure they actually equal the number that you want them to be equal to. So there's a weird property. So what happens? What if a sub 1 of x is equal to 1? What can we say? Say about a sub 2 of x.
Nothing.
Oh, you can say a lot. In fact, you know what it's going to be for sure. And there's a very simple proof. So a sub 1 of x is in here. Is say this is 0 and 1, so x is in here. So let's just do it. And this idea can be generalized to something much more complicated, but we're just doing this simple warm-up example. So that means in this case, a sub 1 of x equals 1. This implies that x is in 1 over beta to 1, right? So then t sub beta of x, right? This is, where is this going to be? So we know that beta x, in this case, is going to be bigger than or equal to 1 and less than beta. So t sub beta of x is bigger than or equal to, let's say 0, right? Because we go mod 1. And less than beta minus 1. So that's fine. I mean, this looks like we have no control over here. It could be anything, but what about beta minus 1? Well, we have the golden ratio there. So remember that beta squared is beta plus 1. I think that's the quadratic for the golden ratio. I could check. So what we do is we want to look at beta minus 1. So let's divide by beta. So I think it works something like this. Beta is equal to 1 plus 1 over beta. So beta minus 1 equals 1 over beta. So this is just equal to 1 over beta. Okay. But what that means then, so if you're here, then you always get sent to this interval. So the image of this interval under this transformation, it just, if you're to place this on the y-axis, right, it's just going to be 0 to 1 over beta. So we have t sub beta of 1 over beta to 1 is just equal to 0 to 1 over beta. So that implies that a sub 2 of x is equal to 0. So you fully know what's going to happen actually, that if you see a digit of 1, then you always know the next digit is going to be a 0, no matter what. Isn't that weird? Now, I just want to emphasize that there may be other expansions. So say you have some real number like this, that's bigger than 1 over the golden ratio and less than 1, something like this. Well, you could have possibly many other sums that give you the same number. But if we're defining this expansion by this algorithm, then you can never see 2 1s in a row. So remember, it's just like a decimal expansion. We sometimes have 2 expansions. With beta expansion, we can have many, many, many expansions sometimes. There's this whole structure of it. I honestly don't remember all the details of it, depending where beta is. Maybe some places have uncountably many expansions or not, or there's a whole big theory of this people have developed. I mean, I'll just be perfectly honest, I don't remember all the details, but if you go to some numeration conference, next one is in Tsukuba, Japan, by the way. I plan on going. The last one was in Utrecht. I didn't make it to, unfortunately, but if you're able to, I know that many of you may not be able to for obvious reasons, but it should be fun at University of Tsukuba. And a lot of people talk about beta expansions. No, yeah, Roman, you were at Rome, and were you at any of the other ones or not? I forget.
In Paris and in
Paris. Oh yeah, Paris. I remember also. Yeah.
Vienna.
Vienna. Oh yeah, because we went to the amusement park in Prater.
Karma Dayani may be the best expert in this direction.
Yes, and she had some interesting things with continued fractions as well. So she's in Utrecht. So I'll write the name out. Let me switch markers. And with him, they have a book also, a pretty simple book, but it's a pretty good read. Core, and then, is it 2 I's? Then, yeah.
Double A.
Or is it double A? Okay. So 2 A's and 1 I? Is that? So.
Should you please demonstrate the intersection of basic intervals of different rank in beta expansion? How can it be geometrically interpreted?
Yeah, and so, yeah, it's kind of just use the idea that we had here, more or less, and just realizing it can be an empty set sometimes, so like in this case. So you basically say, okay, well, if you want to geometrically talk about, say that at level 2, for example, we would take...
In the sense of the decomposition of the unit interval, like like acidic expansion.
Yeah.
Delta 0, delta 1, and so on.
Okay, so let me see, where did I put that over here? So this can get interesting. So this is really simple with a base 10 expansion, but then when we have a beta expansion, we have to be careful. So if we had something like the following, like this is say t sub beta of x, and then we go like this. So maybe beta is something a little bigger. This marker isn't working as well with blue. And then let's say there's a final one right here that doesn't go all the way up, something like this. I think their slopes aren't staying constant. But. Okay, so what's going to happen here? So let's say like you have a digit 1, 2, 3, and 4, something like this. Okay. So when you break this one up right here, so 0, and if you want a 1 afterwards, well, this is going to be pretty simple. This would correspond to 0, 1, 0, 2, 0, 3, and then there's going to be, let's move this over, and then 0, 4, this is going to be smaller. Okay, so there's a 0, 3. And so for these, because this piece is onto, it's pretty simple. So what you're basically saying is you're looking, okay, where do you get this is, if you want the second digit to be 1, you look and see where is this, if this is 0 to 1 over beta. You draw this across right here, and you see, okay, if you project down here, we get like 0, 1, and then down here, we're going to get 1, 1, and then down here, we're going to get 2, 1. Down here, we get 3, 1, and then down here, we get 4, 1. And we keep doing this, so if we have that this is 2 over beta, and then we go like this, and it looks here like we're going to have 4, 2, but this is a smaller interval, at least the way I drew it. And then if we go down here, we have 2, 4, 1, 4, and so on and so on. And so this is going to stop here. The way I drew it, there's never going to be a 4, 3 or a 4, 4. And depending on exactly what's chosen here, you can have more interesting structure popping up. And if you have something, a really weird irrational number beta, then funny things can start to happen. So let me just check and see where we are on time. We only have time. Well, I still want to talk about Lüroth series. So what I just want to say is that we can also talk about normal numbers for beta expansions. There's a special measure. It's a little complicated to write. We're going to call this a Perry measure. This is shown in 1958 to exist by Alfred Renyi. He had a much more general results. But basically, this is going to be the unique invariant ergodic measure that's equivalent to a Lebesgue measure. And so there's a special measure where you say that x is beta normal. If t sub beta to the n x is mu beta at a uniformly distributed mod 1. But like I said, of course, with these expansions, some combinations of digits are not going to show up, and there are theorems classifying this. And just in the interest of time, I want to move on to Lüroth series unless there's any other questions. We just have, if there were like an entire semester, we could really dig into this a lot deeper, but we're just doing a very, very quick overview of a lot of things, and I want to motivate the kind of final results of this little mini course. But there are examples of normal numbers. There's something called the specification property that's very important, and given a certain amount of something called the specification property, you can cook up examples of normal numbers. There can be cases where there are no computable normal numbers, right? Because the problem is there's too many beta. And I didn't mention this before. This is an important thing. For Cantor series expansions, there is a result. There's one by Barros and Barros, where they cook in a special way. So basically kind of what happens is that there's only countably many computable real numbers, and you can kind of find ways to dodge these. And so when you have too many expansions, and this will be the case for like generalized Lüroth series as well, that you can dodge certain numbers and force them to not be normal. So it's kind of in a trivial way this can happen. But it's not given for free that there are always going to be computable normal numbers, and there could be some other unexpected obstacle that may come up and prevent you from writing examples down. But there are, under some conditions, examples of normal numbers for beta expansion that have been written. And this really ugly paper I have that Joseph Van de Heij didn't like, this also kind of has examples in it as well, computable examples. Lastly, let's just talk about Lüroth series. And this is something that admits some interesting generalizations that people, like I said, in this room have dealt with and have said some interesting fractal-like things about that you guys could say much more about it than me from that perspective. And Lüroth series, here we're going to have x can be written in the form of 1 over a1 plus 1 over a1 times a1 minus 1 times a2 plus 1 over a1 times a1 minus 1 times a2 times a2 minus 1 times a3 plus dot 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 dot. And what is the, how do you generate this expansion? You do almost the same thing as with the continued fraction expansion, but you have a different transformation. So you have the same first level intervals. So you go from 1/2 to 1, you go from 1/3 to 1/2, and so on and so on. And rather than having this funny, like negative, non-constant slope, weird thing, this 1 over x mod 1, we connect the dots. We're going to have, this is going to be linear. You start at 0, and then you end at 1. And then this one, you start at 0, and you go up to 1. This one, you start at 0, you go up to 1. Start at 0, go up to 1, and so on and so on. So let's call this Tx. Exercise, right, Tx equals, so write an exact formula for this. It's going to be a piecewise function. So you have countably many pieces, and it's just really simple, just basic algebra, right? You have a point and a point. You just find the formula for the line connecting the 2 points. So this defines this interesting expansion here, and I've seen actually quite a few people that have just independently come up with, let's say quite a few people that care about fractals that have independently come up with Lüroth series without having heard the term Lüroth series. Like at North Texas, I saw a couple of Urbanski students just kind of come up with this idea because they were looking at some fractal type questions and, oh, what would happen here? And so it's actually kind of natural from that perspective to look it up. And what you can do is you can generalize this by, for example, changing the lengths of these intervals and still having countably many pieces, and you can have them switch whether the accumulation point is on the left or the right side. What you could also do instead is you could look at some sequence of intervals, let's say I sub n, where these are all disjoint and the sum of the lengths I sub n is equal to 1. So, and then do the exact same thing, and this will generate something called a generalized Lüroth series. And the thing here is that you can still have a large fractal of points that are not covered. Right? So if the sum of the lengths is equal to 1, that doesn't mean that you cover every single point. You can only know that if they're like ordered, say, from right to left or from left to right. And then you can also do, there's a very unfortunately named generalized GLS. You can look in, I erased their name, but you can look in Dejani and Krykamp's book. So there's a generalized GLS, which is, if you unpack the words, it's generalized Lüroth series. And with that, okay, these are all positive slope. You can also have the slopes be positive or negative, depending which interval they're in. There is one example of that called the tent map that is used a lot in dynamics. So let's say this is 1/2, this is the tent map. And there was actually a problem, I'll advertise this before the next class, due to Sharkovsky and Sivak, so Ukrainians. They had a question that I'll formulate in the next class about generic points for the tent map, and it turns out it can actually be described entirely in descriptive theoretic languages, and one of the many, many things that the theorem I'm going to describe that I have with Dylan Airy, Steve Jackson, and Dominic Kvietniak is we solved the Sharkovsky and Sivak problem, as well as it was a very general result. We wanted to kill a bunch of things at once. But this is a special case. This can be written in a series expansion. This is a special case of a map that can generate a generalized Lüroth series. And so we're just kind of taking what I've shown today as motivating examples for a lot of what we're going to look at tomorrow. So we can talk about normal numbers for any of these expansions. You can talk about a Lüroth series normal number. In this case, Lebesgue measure is the right measure. So Lebesgue measure is going to be invariant and ergodic with respect to this transformation. It's nothing quite so crazy as Gauss measure. So you say that X is Lüroth series normal. if t to the n x is uniformly distributed mod 1. But there are fewer examples of Lüroth series normal numbers known than for continued fraction normal numbers. So, like in some ways, this kind of seems like a simpler thing. The digits are also independent, so you can very easily write down all the frequencies of all the blocks, where you can't do that so easily for continued fraction expansion. But somehow there's some like these deep connections between geometry, like this hyperbolic geometry, and continued fraction expansions and a bunch of other things. And to my knowledge, there aren't as many things like this known for Lüroth series, so I get the intuition that there are less known tools to kind of crack away at this. So, you know, it's also, I believe it's still unknown if you multiply a normal number for Lüroth series by 3 halves or something, is it still going to be normal or not? You know? So there's still some open things there, and as usual, there are many other things I'd like to talk about, but we are running out of time. In fact, we're out of time, so I should stop right now.